Hi, welcome to our EC&M Tech Talk today on medium voltage grounding. First thing we want to do is we're going to go through and clear up a little of the basics on why we have these separate rules for medium voltage grounding. Then we're going to take a look at the individual rules that apply. We're going to find those in Article 250 is where we're going to find those rules in Part 10. So anyway, let's just talk a little bit about medium voltage and where all this comes from. First of all, maybe some terminology, I say medium voltage. I look in the code and it doesn't really say medium voltage, though it does use that terminology in the code here and there. But it talks about grounding of systems over 1,000 volts. And so you could say, well, and then it talks about maybe some, back in Article 495, it mentions something about high voltage equipment and so on. So where are these different voltage levels and what do they apply? The biggest thing I can tell you is don't get confused. Actually, if we were to look at the ANSI C84 standard, it's the standard that breaks down our different voltage levels and classifies them for us down as to low and medium and high voltage and so forth. In our facility distribution systems and so on, we find that medium voltage actually runs from 2,400 volts up to 69 kV. But don't get confused with all of that. When it comes to using the code, just simply look up the information that you need. Use your table of contents, use your index or whatever, and you're going to find out, for instance, that Article 250, of course, grounding and bonding, and then Part 10 is for systems and equipment over 1,000 volts. We also have Article 195, which is for equipment over 1,000 volts and so on. So anyway, just use the code book, okay? Don't get hung up on the terminology. Now let's talk a little bit about some of the reasons as why we have to have different rules for grounding when it comes to medium voltage. First of all, let's take something like maybe some THHN. If I look at this THHN, it's got some 600 volt insulation on it and works fine, right? On systems 600 volts and below, 480, 240, 120, 208, whatever it is. No problems. I just take it, install it in maybe in my conduits or whatever, run it to wherever I need it through my devices and to my equipment, utilization equipment and all of that. And bingo, works fine. That insulation, that 600 volt insulation will keep the electrons, is one way I look at it. It'll keep the electrons on the copper conductor. They won't leak out and go anywhere through good insulation. Also, it's going to minimize any capacitance build up to ground and so forth. And we don't have any real voltage stress to speak of at, below 1,000 volts. Now, once electricity gets up to 1,000 volts, and of course, the higher we go in voltage, the more profound the effects of that voltage will have on our conductors and equipment and systems and so forth. So some of the issues that we run into, well, let's take a look at some medium voltage cable. Here is a piece of 5 kV cable. And so when we look at it, well, it's constructed a little bit different. It's got a lot of insulation on it. And by the way, we've looked at this in previous tech talks. We looked at medium voltage conductors. But it's also got, well, looks like different layers of insulation. And then it's got this copper tape that's actually wrapped around the entire length of the conductor, isn't it? Well, when I start to get to 1,000 volts and 1,000 volts and greater, the higher I go once again, I start to run into some effects. I get some voltage stresses that start to build up. Actually, that voltage is the electrical pressure, isn't it? It's going to want to try and force those molecules of insulation to move and so forth. So it creates some voltage stresses. So I need to get rid of that voltage stress and even it out along my conductor. Also, I'm going to build up a capacitance to ground. And the higher the voltage, the more capacitance to ground I can build up. I'm going to take this conductor and connect it to a piece of medium voltage equipment. I don't want a big capacitive difference between that enclosure and the ground that I'm standing on. And then put my hand on that equipment, right? So we need to get rid of that capacitance between the conductor and ground. Also, we're going to have some current that will leak out. I can't keep all the electrons in the higher the voltage I get. So some of them are going to leak out. And if they leak out, I need to take them where? I need to take them to ground. So in this case, we're using this copper tape, as I mentioned, that runs the length of the conductor. And that's what that copper tape does. I'll go ahead and ground this copper tape. And that way it'll take care of the voltage stresses, it'll take care of the leakage current, it'll take care of that capacitive buildup to ground then. Now, we don't always use copper tape. This is most often what we're going to find, though, the copper tape shielding, the copper shield. Okay? We're going to find this in probably most often in our facilities, where we're running medium voltage systems in our facilities. If I'm running something underground, I may use a concentric neutral where I'm actually using the ground wires that'll be wrapped around, or the wires that'll be wrapped around the outside of the conductor, the insulation I should say, and it'll replace this tape. And those conductors that are wrapped around are going to drain off the leakage current, and they're going to drain off that capacitive effect and all of that. It could also be used as a neutral wire in some applications. So we use that term concentric neutral. I'm not going to use this tape as a concentric neutral, certainly, and or as a neutral. And also I have to be careful. I probably am not going to use this as the equipment grounding conductor either. That would be only special applications. Maybe will I ever do that. Typically, it's just not going to be rated for that. So I guess when I ground this, it's a little bit different then, isn't it? So let's take a look at the rules. Let's move over to Part 10 in Article 250 now and take a look at the rules that apply for grounding of systems over 1,000 volts. So, where do we find the rules for grounding of our systems and circuits over 1,000 volts, or what we often refer to probably as medium voltage when we're working in our facilities? Well, anyway, we're going to look into Article 250, Part 10. That's what it's all about. That's where we're going to find the answers. A little bit of information there in the bottom left of your screen. As you can see, some other references it takes you to. It says, we'll take a look at Article 305 on wiring methods. It says, take a look at Article 315 on medium voltage conductors and cables. And it says, take a look at Article 495 for equipment rated over 1,000 volts. Well, you know what we're going to find is, we're going to find that we're going to be right back here in Part 10 of Article 250. So let's jump into Article 250 and off we go. The first thing we'll look at is Section .180. So 250.180. And here's what it says. It says everything else applies, okay? Then we're going to look at solidly grounded and impedance grounded systems. You see, when we ground our medium voltage distribution systems, we're going to find out that we can either go directly to the ground or we can go through some resistance, which we'd never do in our single phase systems, would we? Less than 1,000 volt systems. So anyway, we'll take a look at those two. We have a lot of medium voltage services out there that the utilities are supplying us, over 1,000 volts, so we'll take a look at that. Mobile and portable equipment, depending on where you work and what you do, maybe mining, you're going to find a lot of mobile and portable equipment. We'll take a look at that. And then for equipment rated over 1,000 volts, it gives them some specifics in 250.190. And then substations, very little information on substations and fences and other metal enclosures and so forth. But we do want to take a look at that and find out that, if we actually build or own a substation, there's a lot more that's involved to it than just what's in Part 10 of Article 250. So let's begin, let's move on. And first of all, we'll take a look at solidly grounded neutral systems then. So by solidly grounded, we just simply mean, hey, there's no resistance that's being added. A good example is over here on the right-hand side. Here we have Y connected. It could be 13.8 phase to phase, 4160 phase to phase, whatever it is. And it's just solidly, that neutral point is solidly connected to the grounding electrode conductor to the earth and ground. Solidly grounded system. And that's probably what we're most familiar with. Now, there's some drawbacks to that. One is we could have a lot of current flow into the ground and we could end up damaging equipment and so forth. So we're going to see in the next section here, we're going to take a look at how we're able to overcome that. Now, one of the things that, for instance, in the panel board that's back behind me, we know that at less than 1,000 volts, we only ground at one point. My goodness, yes. We only ground at that main panel, don't we? We're not going to ground at any sub-panels. We're not going to turn that bonding screw and that enclosure on through and make contact at the sub-panels. The only place we're going to do that is at the main panel. We could call that, or we call that, single point grounding then. We only ground at one point in our distribution system. However, when we're talking about over 1,000 volts AC then, we may end up grounding at more than one point in the system. It's called multi-grounded. So let's take a look and talk a little bit about those rules and what applies then. And so this in your code book is 250.184. Now, as far as the neutral conductor is concerned, it's got to be insulated for at least 600 volts. And it does give some exceptions to the rules, of course, so you'd want to get into that if you get involved in grounding these systems then. As far as the ampacity, it's got to be big enough, the neutral conductor that we're going to use in these solidly grounded systems then. It's got to be large enough to carry the load, which always makes sense. And there's also some requirements as to percent of the phase conductors, what the minimum size is. For instance, in most applications, maybe except for in industrial applications, but anyway, I'm talking 30 to 20% then. So it's going to have to be 33 1/3% of the phase conductor's ampacity, my neutral conductor ampacity is, or, and in certain industrial establishments, it can be only 20% of what the phase conductors is. Now, for single point grounded neutral systems, it's going to give me a total of 8 requirements. And this is subsection B then. And so it tells me things like what can supply my single point system. I have to have a grounding electrode. It talks about my grounding electrode, about my bonding jumpers, about my equipment grounding conductors. The neutral conductor shall only be required if phase to phase or phase to neutral loads are being served. It also talks about the equipment grounding conductor, so you'd want to pay attention to that. It says it has to be run with the phase conductors, and then it tells you, gives you some specifics on that. As far as the last subsection in 250.184, subsection C, and it talks about the multi-grounded neutral system. And it says it's permitted, we are permitted to be grounded at different points along, say, if we have an underground conductor and we don't have the jacket over the conductor, we've just got those stranded wires wrapped around the entire length of the conductor. We can go in and, well, we're permitted to ground those. In fact, we're going to have to every 1,300 feet. It's what it's talking about. But there are exceptions to that as well. So anyway, pay attention on your multi-grounded neutral system, specific grounding requirements on that, especially if you're going underground. Now, the next section that we want to pay attention to is 250.187. So we just talked about solidly grounded systems. Now look at what we're talking about over here on the right. Now we've purposely inserted some resistance between the neutral point in the system and the earth and ground. Less than 1,000 volts. We're not going to do that. No, we're not going to do that, okay? But here we've inserted usually a resistor. It may or may or may not be a resistor. It could be a coil of wire. It could be a combination of a resistor and a coil of wire. In our buildings, in our facilities, indoors though, it's most always going to be a resistor. Depending on the value of that resistor, it's going to limit the amount of current that flows into the earth. So we can talk about high resistance grounding and low resistance grounding. But that's its purpose, to limit that fault current into the earth. And then from there, we go from the grounding resistor into the earth and ground. And so that's no longer the that's no longer the grounding electrode conductor. Once it leaves that grounding resistance, that becomes our impedance grounding conductor then. That runs once again from the bottom of the ground resistor on into the earth. So anyway, it's going to make a difference in how we apply some of our rules, so we have to pay attention to terminology, don't we? So as far as subsection A for location in 250.187, we're only going to find this impedance grounding system in industrial establishments and so forth. We're going to have ground detectors installed in the system, and we're not going to be serving any line to neutral loads if we're using an impedance grounded system. And subsection B talks about the insulation, and so the insulation on the impedance grounding conductor has to be insulated for the maximum voltage down here. And so subsection C is on that neutral point connection, and it says the system neutral point shall not be connected to ground except through the impedance grounding device. So in other words, I can't somehow connect that neutral point, bypass the resistor, and go directly into the ground. I've got to first go through that resistor, is all that's saying. And so subsection D talks about the equipment grounding conductor. It shall be permitted to be bare, shall be electrically connected to the ground bus and the grounding electrode conductor then. Okay. So those are the rules for our impedance grounded systems. Now, as to whether we use impedance grounded or solidly grounded, really that becomes an engineering decision. There's a lot of pros and cons depending on what you're doing as to what you need. So our job is just to go out and install these systems for the NEC then. 250.186 is going to talk about services over 1,000 volts. In our buildings, then, what we often refer to as our medium voltage services. Very common, the utility transformer, they come off of that. They come into they'll step down to our 13.8 or 4160, whatever it is to come into our switchgear inside the building. Data center, we may be up to 35 kV up in that neighborhood coming into the building, something like that, whatever the application is. And what's important to pay attention to is, of course, the service point. At what point do we own the wiring, okay? So that service point, where does the utility wiring connect to our premises wiring system? If that service point is, if we're not grounded at the service point, so we're grounded maybe at that first disconnect coming into our facility and so on, then in that case, we're going to have to run a grounded conductor. This is what's going to tell us in subsection A. We're going to size that grounded conductor based on table 250.102, and we're going to run that grounded conductor from the service point then onto the first disconnecting means. So that's if we are grounded at the service point. Now, if we're not grounded at the service point, then that moves us into subsection B. Subsection B explains that we have to run a supply side bonding jumper if we're not grounded at the service point. So once again, for the particulars, take a look at where you're grounding at your service in these systems, and then get into the specifics of the rules of 250.186 as you need to. Now, portable and mobile equipment. We can find those definitions back in Article 100, right? Kind of the way I look at it is portable equipment, something I can pick up and carry around. Mobile equipment, it talks about in the definitions about it has wheels. There's an example over there on the left-hand side of a piece of mobile equipment because it actually does have some wheels on the back side of it. It's sitting on a trailer, and that's a transformer. And that transformer is supplying some cables that are just laying on the ground out here. And we call those trailing cables. So those are 4160 volt cables. I do believe in that instance. Anyway, they were going to some mining equipment. So a big shovel, and that shovel would move around, and as it moves around, it's got 4160 volt motors on the inside. As that shovel moves around, it pulls those trailing cables behind it. Okay? So, a little bit different piece of equipment, and what we would think about, and oh, you mean you're going to pull this medium voltage cable around on the ground? Sure, we do that all the time in mining applications. So anyway, proper grounding and bonding of the system supplying this mobile and portable equipment becomes important to us. And there are several sections. It talks about impedance grounded systems, the equipment grounding conductor. The maximum ground fault voltage that we ever want to see between the enclosure and ground on this equipment is 100 volts. So while it's a design consideration, we have to install our systems properly. Otherwise, we can get people hurt out there. Now, subsection D talks about ground fault protection. Whoops, there we go. Subsection D talks about ground fault protection. And so what we have to do is we're going to use some protective relaying to sense a ground fault and to de-energize the system, the supply system, that in this case would be supplying our mobile shovel out there. Now, another thing that we'll quite often do is we'll have an additional conductor in a cable called the ground conductor. or excuse me, the ground check conductor. Okay, and so we'll use that to monitor continuity of the equipment grounding conductor. We'll continually pass current from the equipment grounding conductor to this ground check conductor, and if we lose continuity, that'll automatically shut off the supply for us. So a separate monitoring system to do that, but commonly used in mining applications. Isolation is subsection E. Now, if we're going to ground this piece of mobile equipment that you see on your screen, we have to make sure there aren't any grounding electrodes within 20 feet of that, or piping or anything like that. Once again, just a requirement because of the higher voltage levels and stresses and so forth. And then finally, we talk about trailing cable, and we just looked at a picture of some trailing cable. I've got it highlighted there in red. Trailing cables and where we join them together, the couplers, okay? And so it specifically says that for cables, we have to look at Article 400 on cables for any specifics, and we would have to go to the equipment rated over 1,000 volts. Article 495 would cover the couplers. So if you're involved, mobile systems and portable equipment, be sure and pay attention to 250.188. Take a look at 250.190 for grounding of equipment. Now, over 1,000 volts, right? So we have our equipment. This is real important for safety. Of course, as well as all of the NEC is safety related, but certainly 250.190, I think, really becomes important to us. First of all, it says my equipment. Now, we're talking the equipment itself. I have to ground the equipment. So those rules are found in subsection A. So I have to have a grounding electrode conductor, and that's covered in subsection B. And so subsection B talks about, well, just refer back to 250.66 to find out what size grounding electrode conductor you need. And then finally, it talks about the equipment grounding conductor itself. For the equipment grounding conductor, for sizing that, it's going to refer us to 250.122 based on the size of the overcurrent upstream protective device. So those are our rules for equipment in a nutshell, right? And then finally, we're going to combine these last two sections, sections .191 and .194, because I call them, it's for grounding of substations, fences, and other metal and structures. Now, one of the things we have to look at is who owns this equipment. Typically, the utility owns the substation, don't we? And then at that service point, that becomes our premises wiring, and we own everything downstream from there. In some applications, I realize, some facilities, you may build and own your own substation. When it comes to grounding and building substations and how we put the grounding structure underneath on the earth and ground, and multiple ground rods and the grounding grid and the 18 inches of gravel and all that we put on the top, those are all covered separately. You're not going to find those rules in Article 250. Article 250 applies to our premises wiring. So it talks about in section .191 of Article 250, it says that for grounding in a substation, if I have to install a grounding electrode conductor or grounding electrode system, go back to Part 3. Makes sense, so I go back to Part 3, because Part 3 is on the grounding electrode system, right, in Article 250. And so 250.194, sections A and B talk about grounding and bonding of metal fences and the other metal structures at our substation. And it gives some distance requirements. If my fence is within a certain distance of any exposed conductor, or my structures within a certain area, then I have to go ahead and bond to my fence and all of my fence and gates and posts and all of that, and to any of those other metal structures, and I have to connect them to that grounding electrode system down there beneath my substation. And I think we're always going to find out we're doing that anyway, okay? So that is the rules then that we find in Article 250, Part 10, for systems and equipment over 1,000 volts. So that's all the time we've got for today on these grounding of medium voltage systems. The things to remember then, okay? Medium voltage is a little bit different than anything less than 1,000 volts. So don't get confused with the terminology. Go to your code book, use your table of contents, use your index, whatever you need, and find the rules for grounding and bonding at over 1,000 volts. Whether it's equipment, conductors, services, whatever it is, you're going to end up back in Article 250, Part 10 for a lot of it. So pay attention to that. In the meantime, go out there, work safely, follow your NEC rules certainly, and we'll see you at the next Tech Talk.